13.8 Part 1. A local max is a point on a surface from which you cannot walk uphill, while a local minimum is a point on a surface from which you cannot walk downhill. If a point is a max or a min and the partials exist, then both partials are equal to 0. This motivates a definition. A critical point is an interior point where both partials are 0 or where a partial or both partials do not exist. A critical point is a candidate for a local max or min. We're going to find the critical points for this function. Before we find the first partials, I'd like to rewrite the equation. This makes it easier for me to take the derivative. Find the first partials now. Next, we're going to set both partials equal to 0. Both of these equations must be satisfied for a point to be a critical point. We will start with f partial x and build from there. There are three cases to consider when we set f partial x equal to 0. These are our three cases. We will now examine the second equation, f partial y equals 0. We will do that case by case. In case 1, if x equals 1, then in order for f partial y to be 0, it must be true that y equals negative 3/2. Case 2, if y equals 0, then in order to have f partial y to be 0, either x has to be 0 or x has to be 2. Third case, if y equals negative 3, then for f partial y to be 0, either x equals 0 or x equals 2. And these are our 5 critical points. The second derivative test tells us more about these critical points. Before we introduce the test, we need 2 definitions. The first definition is the definition of a saddle point. Intuitively, a saddle point is a point from which it is possible to walk uphill in some directions and downhill in other directions. Given f, we define the discriminant of f in this manner. We are now ready for the second derivative test. If the discriminant is positive, you have a local max or min depending on fxx. If the discriminant is negative, you have a saddle point. And if the discriminant is 0, you don't know anything. We're going to use the second derivative test to classify the 5 critical points of this function. These are our 5 critical points. We have already found f partial x and f partial y. I'd like you now to find the second partials. And here they are. I don't recommend finding the discriminant in this case. It's going to be a fairly ugly function. Instead, what I recommend you doing is building a table. We're going to evaluate fxx for these 5 critical points. And then fyy, and then fxy. We are now ready to find the discriminant for each critical point. Once we have found the discriminant, we need to classify each critical point. Okay, we're ready to classify. If the discriminant is negative, then you have a saddle point. There are 4 points where the discriminant is negative. So each of those 4 points are saddle points. If the discriminant is positive, you either have a local max or min, depending on fxx. We have 1 point where the discriminant is positive, and at that point fxx is negative. So it's a local max. And here is our graph.